Hello students, I am Subhashish. You saw that each rational number is assigned to a point on the number line and learnt about the denseness property of rational numbers. Does that mean the line is filled with rational numbers and there are no more numbers on the number line? Let us explore. Learning outcomes. After the completion of this lesson, you will be able to represent irrational numbers on the number line, to express them in decimal form of irrational numbers, to visualize the real numbers on the number line. Keywords from this lesson: numbers, rational numbers, irrational numbers, factors, integers, decimal, terminating, recurring, natural number. Consider an isosceles right angle triangle whose lengths are each 1 unit long. Using Pythagoras theorem, the hypotenuse can be seen as having a length root over 1 square plus 1 square. Greek found that this root 2 is neither a whole number nor an ordinary fraction. The belief in the relationship between points on the number line and all numbers were shattered. Root 2 was called an irrational number. An irrational number is a number that cannot be expressed as an ordinary ratio of two integers. A natural question is how one knows that root 2 is irrational. It is not difficult to justify it. If root 2 is rational, let it be equal to p by q, where p and q are integers without any common factors, so that p by q will be in its simplest form and q not equal to 0. Now p by q is equal to p by q whole square is equal to root over 2 into whole square, which is equal to 2. From above equation we get p square is equal to 2q square and consider it as equation 1, which means p square is even as equation 2. As a result, p is even as equation 3. Can you prove this? Let p equal to 2m, p square equal to 4m square. This is because of equation 1. Here p square is equal to 2q square. So 2q square is equal to 4m square or q square is equal to 2m square. As a result, q is even as equation 4. 3 and 4 show that p and q have a common factor 2. This contradicts our assumption that p and q have no common factors, and hence our assumption that root 2 can be written as p by q is wrong. That is, root 2 is not rational. Let us see some examples of irrational numbers. Apart from root 2, one can produce several examples of such irrational numbers. Here are few: root 5, root 7, 2 root 3, so on. Pi, the ratio of circumference of a circle to the diameter of the same circle, is another example of an irrational number. E, also known as Euler's number, is another common irrational number. Phi, the golden ratio, also known as the golden mean or golden section, is a number often stumbled upon when taking the ratios of distances in simple geometric figures such as the pentagon, the pentagram, decagon, and dodecahedron, etc. It is an irrational number. Irrational numbers on the number line. Where are the points on the number line that corresponds to the irrational numbers? As an example, let us locate root 2 on the number line. This is easy. Remember that root 2 is the length of the diagonal of the square whose side is 1 unit. How? Simply construct a square and transfer the length of one of its diagonals to our number line. We draw a circle with a center at 0 on the number line, with a radius equal to the diagonal of the square. This circle cuts the number line in 2 points, locating root 2 on the right of 0 and minus root 2 on its left. You started with natural numbers and extended them to rational numbers and then irrational numbers. Representation of a rational number as a terminating and non-terminating decimal helps us to understand irrational numbers. Let us see the decimal expansion of rational numbers. Decimal representation of a rational number. If you have a rational number written as a fraction, you get the decimal representation by long division. Study the following examples where the remainder is always 0. Consider the example 7 divided by 8. Seven cannot be divided by 8, so we add 0. Now we get 70. When divided by 8, we get 64. The remainder is 6. Carry down 0, we get 60. And 8 into 7, which is equal to 56. After subtracting, we get remainder as 4. Carry down 0, we get 40. And 8 into 5, which is equal to 40. And the remainder is 0. Therefore, 7 by 8 is equal to 0.875. Can the decimal representation of a rational number lead to forms of decimals that do not terminate? The following examples with non-zero remainder throw some light on this point. Example: represent the following in decimal form: minus 4 divided by 11. Solution: 4 cannot be divided by 11, so we add 0. Now we get 40 divided by 11, we get 33. By subtracting, the remainder is 7. Carry down 0, we get 70, and 11 into 6 is equal to 66. By subtracting, the remainder is 4. Carry down 0, we get 40, and 11 into 3 is equal to 33. After subtracting, the remainder is 7. Then the decimal form is non-terminating and repeating. Therefore, minus 4 by 11 is equal to 0.36 bar. A rational number can be expressed by either a terminating or a non-terminating and recurring decimal expansion. The converse of the statement is also true. That is, if the decimal expansion of a number is terminating or non-terminating and recurring, then the number is rational. Period of decimal. In the decimal expansion of the rational numbers, the number of repeating decimals is called the length of period of decimals. For example, 25 by 7 is equal to 3.571428, as the length of the period of decimal is 6. Conversion of terminating decimals into rational numbers. Let us now try to convert a terminating decimal, say 2.945, as a rational number in the fraction form. You know that 0.1 is equal to 1 by 10, 0.01 is equal to 1 by 100, and 0.001 is equal to 1 by 1000. That is, in any decimal number, each digit after the decimal point is a fraction with a denominator in increasing powers of 10. Thus, 2.945 is equal to 2 plus 0.945. It can be written as 2 plus 9 by 10 plus 4 by 100 plus 5 by 1000. By making denominators common, we get 2 plus 900 by 1000 plus 40 by 1000 plus 5 by 1000. After adding, we get 2 plus 945 by 1000. Now, by taking LCM, we get 2945 by 1000. By cancelling, we get 589 by 200. Let us see some example. Convert the following decimal numbers in the form of p by q, where p and q are integers and q not equal to 0. 0.35, 2.176 and minus 0.0028. Solution. 0.35 can be written as 35 by 100. By cancelling, we get 7 by 20. .176 can be written as 2176 by 1000, as the decimal form having 3 digits. By cancelling, we get 272 by 125. Minus of 0.0028 is equal to minus 28 by 10,000, as there are 4 decimals after the point. After cancelling, we get minus 7 by 2500. Conversion of non-terminating and recurring decimals into rational numbers. It was very easy to handle a terminating decimal. When we come across a decimal such as 2.4, we get rid of decimal point by just using division by 10. Thus, 2.4 is equal to 24 by 10, which is simplified as 12 by 5. But when we have a decimal such as the problem is that we have the infinite numbers of 4s, and hence we'll need the infinite number of zeros in the denominator. For example, 2.4 is equal to 2 plus 4 by 10. Two 2.44 is equal to 2 plus 4 by 10 plus 4 by 100. Two 2.444 is equal to 2 plus 4 by 10 plus 4 by 100 plus 4 by 1000. How tough is it to have infinite 4s and work with them? We need to get rid of the infinite sequence in some way. The good thing about the infinite sequence is that even if we pull away 1, 2 or more 4s out of it, the sequence remains infinite. Let x equal to 2.4 bar as equation 1, then 10x is equal to 24.4 bar as equation 2. When you multiply by 10, the decimal moves one place to the right, but you still have infinite 4s left over. Subtract the first equation from the second. Subtracting the first equation from the second, we get 9x is equal to 22. Where x equal to 22 by 9. We use the same logic to convert any number with a non-terminating repeating part into a fraction. Example: convert the following decimal numbers in the form of p by q, where pq belong to integers and q not equal to 0, 0.568 bar. Solution: let x equal to 0.568 bar, which is equal to 0.5686868 as equation 1. Here the repeating decimal digit is 68, which is the second digit after the decimal point. So multiply equation 1 by 10. We get 10 into x is equal to 5.686868 so on as equation 2. Now period of decimal is 2. Multiplying equation 2 by 100, we get 1000x is equal to 568.6868 so on as equation 3. Subtracting equation 3 and 2, we get 990x is equal to 563, where x equal to 563 by 990. Decimal representation to identify irrational numbers. It can be shown that irrational numbers, when expressed as decimal numbers, do not terminate nor do they repeat. For example, the decimal representation of the number pi starts with 3.141592 so on. But no finite number of digits can represent pi exactly, nor does it repeat. Consider the following decimal expansions: 0.1011 so on, 3.0120 so on, 12.2302 so on, root 2 is equal to 1.4142 so on. Are the above numbers terminating or reoccurring and non-terminating? No, they are neither terminating nor non-terminating and reoccurring. Hence, they are not rational numbers. They cannot be written in the form of p by q, where pq belongs to integers and q not equal to 0. They are irrational numbers. A number having non-terminating and non-reoccurring decimal expansion is an irrational number. Points to remember: an irrational number is a non-terminating and non-reoccurring decimal, that is, it cannot be written in the form p by q, where p and q are both integers and q not equal to 0. The union of all rational numbers and all irrational numbers is called the set of real numbers. Every real number is either a rational number or an irrational number. If a real number is not a rational number, then it must be an irrational number. Thanks for watching.